And here is the other hardness test. Some of the other ones, you know, Burnell, again, he's talking about that. You see Vickers hardness test, use a pyramid indenter, diamond pyramid indenter, man-made diamond, by the way. Knoop hardness test. You have Rockwell hardness test, and you get different types of loads and different types of indenters that they use. And there's a lot of other tests. You might have heard of Mohs scratch test before in geology, right? And they do that. That's also a form of hardness test, you know, diamond being the hardest. Then this is the correlation between strength versus hardness here. You see here the tensile strength here, and here's Burnell hardness, and you see that almost like a straight line, right? Correlationship. So when the hardness goes up in material, the strength goes up, you know, so that definitely we can look at that. Another thing related to the steels, because you got to have some background in materials, and you know, I know our students do take material science class, but this will be helpful already, and there's always more to study. You can get a PhD in metallurgy alone, you have PhD in ceramics, you have PhD people, polymer people. It's, you know, like anything else, it's amazing how much material and knowledge is out there. Just, you know, this is an example here of phase diagrams. Okay, the iron carbon phase diagram, and you see here two variables I have here: the temperature, and then you see here the weight percentage carbon here. And you know, they could have had another variable to make it three-dimensional, like pressure. Usually we keep pressure, all the processes usually done in the steel mills and all that are done at atmospheric pressure. So, you know, but if you start to talk about the forming of like diamonds and all that, pressure has something to do with it also, right? But most industrial processes, we have two variables that we look at: temperature and weight percent carbon. Temperature we can either measure in degrees Celsius, we can measure it in degrees Fahrenheit, so we use the two scales. And then here's the weight percentage carbon, and it goes from left to right, from 0, and usually we go to 100, but what they found out is for the steels and the cast irons and all that, if you get too much carbon in it, it becomes just way too brittle, so they don't even want to mess with it. And that's why the diagram already stops here. This is 6.67% carbon. There's the intermetallic compound, iron carbide or cementite. You know, that's why we stop there. And then here, in this phase diagram, you see a lot of different, what they call phases, right? And a phase is basically a chemically homogeneous, distinctible form of a material. Like, I like to think of it like, if you take, let's say, oil and water, okay? What does oil do when you have oil and water? Usually floats on top of water, right? Like oil will float on it. But in two different phases. But if you have alcohol and water, what happens? You mix it and you can't even tell the difference between one phase, right? Well, here we do what he's not mentioning here. He mentions here the weight percent carbon. Well, what is he not mentioning? What was steel again? Iron, right? He's not mentioning the iron, but there's actually two elements in that. It's understood that we also have, you know, if I have 1% carbon here, that means I have basically 99% iron. That's not exactly right because there's alloying elements in there, but it's understood, you know. A lot of phase diagrams, they will put both phases in there. If you talk about the lead tin diagram, they will put PB, plumb, and tin in there, stannum, right? But here they just list the one phase, but it's understood that the iron is the other phase. Now, you see here a bunch of different phases here, and they call this the alpha phase, okay, which is called ferrite. And you know, we can talk about crystal structures when we talk about metals. That has what they call a body-centered cubic crystal structure, okay. And the gamma phase here, that's the austenite phase. It has a face-centered cubic structure. And then you see here the Fe3C, you know, they call that cementite or carbide, okay, which is an intermetallic compound. Like if you look at this region here, what do you have there? You got the ferrite and cementite, right? There's actually two separate phases in there. They're really, if you start looking under a microscope, you can't see those two different phases, okay? Here, you have just one phase here, that's the alpha phase, which is ferrite. You know, it's just basically all iron and a little bit of carbon. You get the maximum the maximum dissolvability of the carbon is 0.02% carbon. Now here you see the austenite region, right here, right? And the maximum dissolvability of carbon into the austenite region happens at about 1148 degrees Celsius or 2098 degrees Fahrenheit, and that maximum solubility limit is 2.11%. Right? Then you see here again two-phase regions. You see gamma plus liquid. Anytime, by the way, when you see Greek letters, there are solid phases. You know, the other ones are liquid phases. Here you see, so here you have kind of a slurry of a solid phase and a liquid phase. Now above here, what do you got? You got all liquid, right? Then, interesting here, this is the cutoff point. If you had a straight line, 2.11%, and it's an artificial cutoff point, but it's because of that solubility, so maybe not totally artificial. On this side, we consider them steels. If you go beyond 2.11%, those are considered cast irons, okay? Like cast iron, you know, the word cast means you can pour it easily, right? Make a casting, right? Well, they have, you know, pretty low melting points. You see here's the liquid phase. You had 4.3% carbon if you had that, you know, and at a temperature of 1148 degrees Celsius or 2098 degrees Fahrenheit, you go immediately, you cooled it down, if you're liquid and you go straight down, you get what? Two solid phases, right? Immediately, but separate phases, you can't tell by the naked eye, okay? But if you start looking under a microscope, you can see that. We have a microscope in the lab that we just put like 1,000 times magnification, and you can see the different types of phases, do like metallography, right, looking at microstructures. And I know there's an overlap with this, with geology and all that stuff.
Mineralogy.
What's that?
Mineralogy.
Mineralogy that you guys probably get on very deep and all that stuff. Right? Yeah. And then here you see some delta ferrite, which is not that significant and not much industrial importance. But this is an important point here. This 0.77% carbide. If you took a steel exactly of 0.77% carbon right here, right? And you were at this temperature, let's say 1,000 degrees Celsius, and you cooled it down, then what happens over here? If you go down a little bit more, what do you get? Ferrite and cementite. And that is what they call pearlite. That microstructure is called pearlite, which is a special type of microstructure, and I can show you that here. That's what it would look like. That's pearlite. That's the microstructure you get. So people can go back here. I kind of took that same picture there, and from the source, and you see here again the 0.77% carbon. If you cool it down, here this line X, and you go to X prime. If you cool it down slowly, because that's what phase diagrams do. Phase diagrams or equilibrium diagrams, you have to cool things down slowly. If you start cooling things down fast, you cannot use the phase diagram anymore. Okay, to predict the results, you have to use other type of diagrams. But if you took this here, this austenite, cooled it down, you get ferrite and cementite, right? And that's called eutectoid composition. Any steels that have less than 0.77% carbon are called hypoeutectoid steels. Steels that have more than 0.77% carbon are called hypereutectoid steels, right? And if you wanted to look at microstructures, you would see actually if you have a eutectoid steel, that 0.77% carbon, and you cool it down slowly, you see the pearlite. They call that pearlite, and the white regions would be the ferrite, and the darker regions would be the cementite in this picture here. Now the hypereutectoid steels, what did they have? They had more or less than 0.77 carbon. More, right. Then you get still a lot like pearlite, you get that, but you get also here the white regions here more cementite, because you were if you had a hyper-eutectoid steel, you're here on this side of the diagram, right? So when you cool it down, it goes through austenite, and you get austenite and cementite. Well, if you cool it down more, you're gonna get a little bit of that, you're gonna get that perlite and more cementite. So that's why the microstructure looks different. Now for the hypoeutectoid steels, they were over here on the 0.77% carbon on this side, below this side, we'll see this. See the photomicrograph of a hypoeutectoid steels. Now what are you gonna get there? You're gonna get perlite, just like that, and then the white regions, they are like the ferrite, because if you took a steel, a hypoeutectoid steel, you start out with austenite, you cool it down, you're going to get first ferrite and austenite, and then, if you cool it down more, you're going to get perlite, a lot of that, but you're also going to get a lot of ferrite in there. That's why you have that mixture. So, that's kind of an important point right there. Then, in steels and cast irons, we do a lot of times a lot of heat treatments, okay? And we can change the properties of materials, right? And basically we distinguish between two types of heat treatments. We have the processing heat treatments, and we have the strengthening heat treatments. Well, processing heat treatment means that we're going to make it easier to do the next process on it. So that means maybe we want to form it, we want to soften it up, right? Form it or machine it. If you have a real hard steel, if you can make it a little softer, then you can cut through it easier, right? Or if you did cast it or you did weld it, well, you have a lot of stresses in the materials. A lot of warping might actually occur. Well, by giving it a heat treatment, you can relieve the stresses out of the material. Okay, so that's they're heating it to high temperatures, these processing heat treatments, but then they're cooling it slowly, okay? Where in the strengthening heat treatments, okay, what they do there, they make like tempered steel. You might have heard of tempered steel. What they do there is they heat it up to real high temperatures, and then they quench it real fast, okay? And they get basically an unstable structure. It's called martensite. And it's very hard, very strong. Unfortunately, it's very brittle. So then you have to reheat it to relieve the stresses and let the carbon diffuse out of that microstructure. That's unstable, that's stable, and then make a stable structure. So that's called tempered steel. Now here we have some of the temperatures that we would have to heat it up for the processing heat treatment. There's a bunch of different types of processing heat treatments available to the heat treater. And again, you see the steel diagram here, the temperature, degrees Celsius, degree Fahrenheit, 80% is carbon. And you see here some different types of heat treatments, like you see annealing, that's softening, okay? Now this tells you only, this diagram, the temperatures that you gotta heat it up to, okay? Like, for example, if you had a 1060 steel, that means 0.6% carbon, and you wanted to do an annealing heat treatment, well, you would have to heat it up in this range here. That's about, I would say about close to 770 degrees Celsius, right? 1400 degrees, a little bit higher, 1500 degrees Fahrenheit, and then hold it there for a while. Now, how long do you have to hold it? That depends on the thickness of the metal. Okay, when a heat treater does this, they look at the thickness of the metal. The thicker it is, the longer you got to hold it there to, let it heat through. Always the surface will heat up real fast, but the inner part takes a little bit longer, right? And then you have to cool it down slowly, okay? The difference is, for example, like a normalizing, which is another heat treatment.